very interesting, but you still have to get them out the ground. You still have to be able to purify them so that you can use them. And the problem is they've got a similar ionic radius. They've got the same valence state. So that equates to similar chemical behavior. So they all behave as if they are 15, I don't know what you call 15 twins, but this is how they behave. And therefore, it's extremely difficult to separate them from each other because the differences are so small. But, thank heavens, nature provides us some assistance in the whole process. We have a non-natural occurring element there in the middle called promethium. It doesn't exist naturally, so it leaves us a gap that we can use to separate at least certain groups from each other. So there's promethium between the light and the middle rare earths. Then there are two other rare earths that are not happy in other oxidation state, but at least you can get them into other oxidation states. That's cerium, that is relatively stable in the 4th valence state, and then europium that you can reduce to the 2 valence state. Then electronegativity, because the ionic radius decreases and the charge stays the same, electronegativity increases. So these are 3 things that one can use to separate the rare earths from each other. So I'll tell you now how we use that. First of all, to explain that rare earths are processed and separated by solvent extraction. This is the most common technique at the moment to separate them. You can do it in other ways, but especially when you have large throughputs, solvent extraction is attractive. As you see the rare earths as they go along the series, the extractability increases, and the equilibrium pH goes the other way. So that H, that proton there on the extractant, becomes more and more acidic as you move that way. So you basically have a knob that you can turn to separate this, and that is the pH when you want to separate them from each other. Right, so this is the scheme. This is how we use these assistance, bits of assistance that nature has given us. First of all, we obviously crack the ore, and then we dissolve the rare earths out of them. Now we have them in a liquor, and first thing that we can do is we can precipitate them as a hydroxide. So you push up the pH, and they precipitate as an hydroxide, and you leave quite a bit of impurities behind. So now you have an impure rare earth oxide, hydroxide. So then what you can then do is you do an oxidative drying. So you dry it under the influence of an oxidant like oxygen, push up the temperature. It's nice to have a dry material to work with. And at the same time, while you dry it, the cerium oxidizes to cerium 4. Okay, all the other rare earths stay in the 3rd valence state. Cerium goes to 4. Then you redissolve that lot, the hydroxide. Now cerium in the 4 state doesn't dissolve now. All the other rare earths dissolve, so now you've gotten rid of cerium. Now you've got another little gap that you can use to separate. So promethium fortunately was there already, so there's a gap. And now the redissolution of after oxidative drying, you've got a gap for another gap caused by cerium. Now you can separate the different groups from each other by controlling pH of the solvent extraction process. So you've got lanthanum sitting by its side now that you can separate relatively simply, and you've got praseodymium and neodymium sitting together. Okay, and you can separate then the middles up to terbium from dysprosium. So you've got that as your rough separation step. Controlling the pH even further, you can now separate praseodymium and neodymium from each other. Although for magnetic materials, most magnet manufacturers take it as it is in the natural ratio. because you need both of them in a magnet. So it is actually not necessary to separate them from each other, but you can if you wanted to. Then you've got basically three groups. The light ones, that the lanthanum is normally used for catalytic purposes. You've got that separated. The praseodymium, neodymium for magnets. You've got that separated. And then you've got the middles and the heavies. And you can then separate the middles and the heavies from each other, either by controlling the SX process extremely tightly on pH, or by means of ion exchange processes. The concentration in the ore of going from lanthanum to lutetium, for instance, cerium is the most abundant. Lanthanum is also very abundant. The middles and the heavies, there are very little of those elements in there. So ion exchange is ideal to separate them. Okay, so the long and short of all that is it makes for an extremely complex process. Most refineries have banks of 200 mixer settlers just to separate certain bits from each other. So it really makes, even if you use this scheme, it makes for very, very complicated separation. So how much does such a refinery cost? Can we do it in South Africa? This is the next question that we've got to ask. We know it's difficult. We know we don't have great rare earth resources. Can we do it in South Africa? So the first problem statement is, how much does it cost? Because it's so complex, it's also very capital intensive. And if you want to achieve the best economies of scale, you need to look at about 10,000 to 20,000 tons per annum. As you can see, the Molycorp Mountain Pass refinery and liners, both are around 20,000 tons per annum, because that's a sweet spot in terms of economies of scale. But have a look at that, $500 million US. That's what it costs. That's a picture of Lynas refinery. You can see banks and banks of mixer settlers sitting there. That's a view of the whole site. It's expensive. It costs about $500 million. So the bottom line is, if you want to support such a capital investment, you have to have a deposit that's large enough that will be able to supply such an investment for 20 years. If you don't, you're essentially dead in the water. You cannot, or you should not, invest such capital. So problem statement 2 for South Africa. Okay, so there's a lot of money that we need to invest. Second problem statement really is, do we have the rare earths to do this? I've told you about Steenkampskraal, Zandkopsdrift, and there are several, but they're all small. Have a look at that. 0.03 million tons. Zandkopsdrift, some people say 500,000 tons, some say 900, but it's still not enough to support a refinery of 20,000 tons per annum for 20 years. Steenkampskraal would be done in 2 years, if you have that. So it presents a bit of a problem for us. Problem statement 3, complex technology. Do we have this in South Africa? Can we actually develop the technology to do this in South Africa? It's also a question to be answered. So again, can we do it in South Africa? I do believe we can. I think we can address problem statement 1 and problem statement 2 by establishing a centralized refinery. So we can now construct a refinery with the required economies of scale, anything from 10 to 20,000 tons per annum, and we can then take feed from different deposits. But there's a catch. Because of the variable deposits, there must be a step in between where we sort of equalize the feed to a refinery. You can't just toss anything that you like into a refinery. So that is where we have this process, the chemical rare earth concentrate This is a step that one should have to get the feed material in a consistent state so that you can feed a refinery to separate them. So if we have a centralized refinery in South Africa, if we build that, we can treat the variable concentrates. I believe we can. We will have the economy of scale. South Africa has the infrastructure. South Africa runs PGM refineries, very complicated refineries. We have the infrastructure, we have the skills to run that. I believe we do have that. Chemical supply, again, our industry is well developed. The supply of chemicals, not a problem in South Africa. We have a good transport infrastructure. We have established areas where we can build such a refinery. Saldanha comes to mind, Richards Bay comes to mind, Kruger comes to mind. These are all areas that are zoned as development areas, and there are breaks, tax breaks, and other incentives to establish there, and so it has the infrastructure also and harbors to export. So I do believe if we look at the concept of a centralized refinery, we can certainly overcome problem statement 1 and problem statement 2. There are ever critical issues to be addressed for such a centralized refinery. So planning of the feed has got to be important, because you're going to have a lot of producers producing ore, and there has to be a very good plan so that you never run out of feed. So that's going to be important. And it's critical to know, it's critical to know what your feed is going to look like. But if you do have this step that you can equalize and stabilize, make the feed consistent, that should take care of a consistent feed. The other thing is the offtake agreements. Until South Africa has established a firm rare earth industry, making magnets, catalysts and so on, it's important that you secure takeoff, that you don't sit on your production. So that is quite important. The other thing is rare earth prices are very volatile, and they're very difficult to market. So these are critical things that we've got to look at. But I do believe one could find partners to do this. Equity obviously is key, and financing will be key. So I really don't see that we will ever establish such a centralized refinery without essentially a strategic national view of such a refinery. And the other advantage, I won't speak for Nexa here, but I do believe with Steenkampskraal being a thorium mine, we have a place to actually store the radioactive waste. We won't talk about foul pits at all, but at least Steenkampskraal being a thorium mine, being a radioactive area, there's an opportunity there. Not every country has that ability to do that. Okay, the benefits of a centralized facility, obviously I said economies of scale, costs of reagents and processing is there. We have a developed infrastructure in South Africa with sophisticated operational support. We have access to reagent production and recycling facilities. South Africa still has qualified staff. We are running, like I said, PGM refineries, and we have a centralized storage for wastes. Right, so problem statement 3, can we do it? Do we have the technology? Well, Mintek has been working on rare earths since the 1960s. And you can see, I've just drawn a bit of a curve to show the effort that we've done over the years, and that was largely dependent on interest in rare earths. In the 60s and 70s, there was a big interest. Then it waned a bit, and it was up and down, up and down. In around about 2010, when the prices shot up by thousands of percent, there was obviously a huge interest again, and Mintek started investing heavily in rare earth technology. We had the very good fortune that we worked on essentially every single rare earth project on the globe, including Mount Weld, Mountain Pass, except obviously China. They are very closed when it comes to that. But so we had this benefit of doing commercial work for just about every deposit of the world in the world, and obviously, you do build up the expertise as you go along. We've also invested heavily state funding in developing the technology to process and refine rare earth elements. These are just a couple of pictures we piloted this process that we developed, completely piloted it from the cracking stage right through to separating all the rare earths from each other. There's a picture of our pilot plant that we built at Mintek. At the bottom you can see our control system. We had to control that plant at 0.02 pH units in order to separate them from each other. So it's extremely tight control, but it can be done. So the bottom line is Mintek has developed the technology to process rare earths up to front-end engineering design stage. So we could basically hand over to an engineering company and they can build a plant. So I do believe we have the technical ability to do that in South Africa. So if you then summarize and conclude the story, we do believe we have the technical expertise in South Africa to build and support such a facility. We do believe we have governmental support to do something like this. We certainly have the infrastructure in South Africa. We know how to treat the waste and the radioactive materials. So South Africa may not have world-class rare earth resources, but again, we're not worse off than anybody else, really. We also believe there's probably a space for one more world-class producer in the next 10 years. So you can ask yourself, Russia can do it possibly, Brazil could possibly do it, but again, why not South Africa? We are in no weaker position than anybody else. It would just require perhaps a strategic will to do this. I believe we have everything that we need to develop a rare earth industry in South Africa. Thank you.